So good morning, students. Let's proceed with the standard random variables which we started off yesterday. So as you can see on the screen that I had explained you what these standard PDFs are and gave you an example of the Gaussian PDF, which is used for population approximation of finding the population. So it is also known as hypothesis. Then we started off with the first standard random variable, which is the uniform random variable, and it lies between x1 and x2. I also explained you how we had already done this in the characteristic functions, where x1 was a and x2 was b, right? So we had been given the are you able to see the screen?
No, sir.
Okay, 1 second. Okay. I think now it's visible, right? Is it visible? Anyone?
Yes, sir.
Okay.
Yes, sir.
Okay. So we had the graph which I am drawing on the left hand side. We had done this during the characteristic functions, where the PDF was lying between the points A and B, but we have taken x1 and x2 to find to define the PDF. So you can see that this is the PDF which is defined, and from here using the relation between CDF and PDF, we were also able to find the CDF, right? So this was the CDF here. Okay, and then I've drawn the CDF for you and shown you how that CDF looks like. Then we found the mean value, which comes out to be x2 plus x1 by 2, or if it the PDF is given in terms of B and A, that is starting point is A and ending point is B, then mu x will simply just become B plus A by 2, right? So here we have just taken x1, x2, you can take B and A. And then I had asked you to solve for the variance, so I'm hoping that you have done it. We'll be doing that today, so you can check the answer. Then we move to the exponential random variable, which is given as lambda e raised to minus lambda x. So this is the PDF, and we had already done the characteristic function for this exponential random variable, and the CDF is what we found yesterday. So the CDF is given as this function fx of x here. So this is the CDF, and then we have drawn the CDF and the PDF. We found the mean value for which you could use any of the techniques. I had suggested that you could use the technique of integration by parts to do it. So I'm hoping that you have done the mean and the variance values, right? So let us first take the first part which I had asked you to do, that is the variance of uniform distribution. Okay. So for reference, we had already found the mean value. So I'll write it here. Mu x is if I take b plus a by 2. Okay. B plus a by 2. Okay. You can also write this in terms of x1 and x2. Okay. So now we are our aim is to find the variance. So sigma x square, which is e of x square minus mu x the whole square, which will be equal to e of x square minus b plus a by 2 the whole square, right? So we already know the second term, so I've just substituted. All we need to do is to find e of x square, right? So how do we find e of x square? So the formula is e of x square will be negative to positive infinity x square fx of x dx. So e of x square. Now I'll substitute the limits. The limits are between a and b, or x1 and x2. Okay, and you have x square, and fx of x is 1 by x2 minus x1, or 1 by b minus a. 1 by b minus a dx. Therefore, this will become 1 by b minus a, which I'm taking outside the integral, and you'll have a to b x square dx. Therefore, e of x square here will be 1 by b minus a, and you'll have x cubed by 3 going from a to b. The limit going from a to b. So therefore, e of x square will be 1 by b minus a. Now we'll substitute the value. So you'll have b cube minus a cube divided by 3. So now I need to know what is this b cube minus a cube, right? So b cube minus a cube can be written as b square plus ab plus a square divided by I'll take the 3 and b minus a together. This is your e of x square. So from here we can get sigma x square, which is e of x square minus mu x the whole square. So I'll write e of x square, which is b square plus ab plus a square by 3 into b minus a minus b plus a by 2 the whole square. So now we need to solve this, and once you solve this, you'll get your sigma x square. So this sigma x square, now we'll take the LCM and do it. So you'll have 2b square plus 2ab plus 2a square minus 3 into b minus a into a square plus b square plus 2ab, and this will divide with 6 into b minus a. So now you need to multiply this, plus 2ab plus 2a square minus 3, and you'll have a square b plus b cube plus 2ab square minus a cube minus ab square minus 6a square, and this will divide itself with 6 into b minus a. Right, so I've brought this to a very simplistic equation, and another couple of steps and you'll get your answer. So at the end of the day, the answer which you will get for the variance will be b minus a the whole square divided by 12. Okay, so I'm just letting out 2 steps which you can solve yourself, the next 2 steps, and you'll get your answer, right? So for a uniform random variable, the PDF is defined, the CDF is defined. Now we have found the variance, and the mean value is b plus a by 2. So if you are given a numerical where the random variable is uniform, you can directly use these values, right? You can directly use these values and get your answer. So let's take a numerical and you'll understand what I'm trying to say. Okay. So this numerical is based on uniform random variable. So it's a very simple numerical. Any questions?
Sir,
Yes.
yes.
Any questions? If there are no questions, please keep yourself muted. Please keep yourself muted if there are no questions. Okay. Okay. So let's just look at this question. It says over the interval, and the interval is 0, 25. In this interval, the PDF is given as f of x is 1 by 25 minus 0 for 0 less than equal to x less than equal to 25 and 0 otherwise. So it says find the mean value and the variance value, right? So you can relate this PDF. So let me write it on the left hand side for reference. So you can relate this PDF to the uniform random variable because it looks like this. It is of the form 1 by b minus a for a x between a and b and 0 otherwise, right? So in this case, b is 25 and a is 0, right? Therefore, you can use the mean value. You can find the mean value, which is b plus a divided by 2. So you'll have 25 plus 0 divided by 2. So you'll get 12.5, right? The mean and variance is always going to be a constant value, okay? And sigma x square, which is b minus a the whole square divided by 12. So you'll have 25 minus 0 the whole square divided by 12. So if you do this, okay, so you get 52.08. So this is a very simple problem that we can solve, and with this you can also find the CDF value, right? So we have done this keeping a and b or x1 and x2 and found the CDF for uniform random variable. Instead of those values x1 and x2, just substitute x1 as 0 and x2 as 25. You'll get your CDF answer, right? So I hope this was clear how we could use this. Okay, so next we wanted to calculate the mean and the variance value for an exponential random variable, right? So let me rewrite that exponential random variable. You had fx of x as lambda e raised to minus lambda x for you can write it both ways. I'm going to write it as x greater than or equal to 0. You can also write this as 0 less than x less than equal to infinity, right? But I'm just going to write x greater than or equal to 0, right? And 0 otherwise. So for this, we have to calculate the mean and the variance value, right? So let us first look at the mean value. So I need to find mu x. So mu x is integral x fx of x dx going from minus to plus infinity. Therefore, now the limits for this particular problem would be 0 to infinity x into lambda e raised to minus lambda x dx. We'll get the lambda outside the integral. It's a constant, so 0 to infinity x e raised to minus lambda x dx. So now we can use the integration by parts. So I'm hoping that you've gone back and looked at it. So I've already solved it. So I'm just going to write the equation by parts. Please check it. Okay. So lambda is the constant outside, and then we have x e raised to minus lambda x divided by minus lambda. So you have x integral e raised to minus lambda x, that's the first term, minus integral 0 to infinity e raised to minus lambda x divided by minus lambda dx, and this goes from 0 to infinity, right? That is your integration by parts. So mu x will be the lambda is outside. You have x e raised to minus lambda x divided by negative lambda minus, now we'll integrate this again. So you'll have e raised to minus lambda x divided by, you have another negative lambda, so this becomes lambda square, and this goes from 0 to infinity. Therefore, mu x will be lambda is outside. Now we'll substitute for the infinity part. So you'll have 0 minus, in the second term you'll have 1 by lambda square. Therefore, you get lambda divided by lambda square. There's a negative term here. So you get lambda divided by lambda square, which is 1 by lambda. Therefore, the mean value for an exponential random variable is 1 by lambda. Okay. There are other methods also to find this integration, but integration by parts is, in my opinion, an easier method. Next, we need to find the variance value, that is sigma x square, so which is E of x square minus mu x the whole square, which can be also written as E of x square minus, we've just found the value of mu x, which is 1 by lambda, so we'll have 1 by lambda whole square. So the only job to be done is to find E of x square, which is given as negative to positive infinity x square fx of x dx. You can change the limit 0 to infinity x square, and the PDF is lambda e raised to minus lambda x dx. Therefore, E of x square will be integral 0 to infinity. I'll get the lambda outside, and you'll have x square e raised to minus lambda x dx. Now we can again use integration by parts to solve for E of x square, right? So we can treat x square as some u and e raised to minus lambda x as v. They're also known as the uv rule. Okay. So you'll get here, so you have u as it is, that is x square e raised to minus lambda x. There should be an integral for e raised to minus lambda x. So you get e raised to minus lambda x divided by negative lambda minus integral 0 to infinity the differential for x square. So you'll have 2x. In the previous case we just had x, so the differential was just 1, that's why we have not written. Here you'll have 2x, right? And you have e raised to minus lambda x, the integral divided by negative lambda dx, right? So I'm doing this under the assumption that you're aware of the uv rule. Okay, if not, please go back and see. And then therefore e of x square will become lambda into x square e raised to minus lambda x by negative lambda. The first term is as it is, minus, I'll get the 2 outside by negative lambda outside. We'll have integral 0 to infinity x e raised to minus lambda x dx, and this will go from 0 to infinity. Now this x e raised to minus lambda x integral we had found in the previous case when we were finding the mean. We had to apply the uv rule. So you're applying two uv rules there, right? So that answer, this x e raised to minus lambda x, this part here, which we had found previously, we found out that this is the mean value there. So this value is 1 by lambda, right? So what we'll get at the end is here lambda as it is, x square e raised to minus lambda x by negative lambda, the first term is as it is, minus 2 divided by minus lambda, and that integral as I just specified is 1 by lambda, right? So that integral is just 1 by lambda, and all of this goes from 0 to infinity, right? Therefore e of x square, now we'll start putting the limit. So the first limit is just going to be 0. So what you will get is what you'll get here is 2 by lambda into 1 by lambda, which will give you 2 by lambda square. So this is your e of x square. Therefore sigma x square is e of x square, which is 2 by lambda square, 2 by lambda square minus mu x the whole square, which is 1 by lambda square. Therefore you'll end up with 1 by lambda square. So sigma x square, the variance for an exponential random variable, is 1 by lambda square. Okay. So just for your reference, because I've used the UV rule, I'll just mention it here. So it's like a revision for you. If you have integral u v dx, then this can be written as u integral v dx minus integral u dash is the differential for u into integral v dx, and this entire thing will be dx. So this is your uv rule, or by integration by parts, which I have used. Okay, this is known as the uv rule or integration of parts. Here again I repeat that dash is the differential, the first derivative. Okay, so we found the mean and the variance value for the exponential and the uniform random variable. So likewise we can do this for all the random variables which we have. You can also find through the characteristic equation all these values. Okay, so let us look at the next one, the next random variable. So the next random variable is a very important random variable. Okay, and that random variable is known as the Gaussian random variable. Okay. So this is known as the Gaussian random variable or Gaussian distribution, and it is given as fx of x is 1 by sigma root 2 pi, where sigma is the standard deviation, exponent of minus x minus mu the whole square divided by 2 sigma. Okay, so right now you must be thinking that it is very difficult to this should be 2 sigma square. So you might be thinking that it is too difficult to remember this, but don't worry about it. We'll be doing this so many times that at the end of the day you will remember what this random variable actually looks like. Okay, so this is a very important random variable, and this happens, this PDF is for negative to positive infinity. So there is no zero value here. So this goes for x between minus 2 plus infinity. Okay. Now the mean value. Okay. I'm not deriving the mean value because you can see here that it will be complicated to integrate this and find xfx of x dx. If time permits, later on we'll find out, we'll derive what the mean value is. Okay, so the mean value for this random variable is just mu, which we have written here, that is this part here. Okay, and it's sigma x square, the variance value is just that sigma here, that is sigma square, right? So to avoid confusion, I'm just going to write the mean of the Gaussian random variable is mu, and the variance of the Gaussian random variable is sigma square. Okay. Now this random variable is important because this Gaussian random variable converts into a normal distribution or normal PDF. The name is normal distribution or normal PDF when the mean value mu is 0, right? So in this case the mu becomes 0, that is the mean value is 0 and the variance remains sigma square, and it is denoted as n0 comma sigma square. So we'll solve numericals later on, and you'll see if it is specified that it is normal distribution, we can take the mean as 0 and variance as sigma square, right? Whereas for the Gaussian case, which we discussed earlier, you can write this as G, which represents Gaussian, mu comma sigma square. Okay, so I'm not deriving the mean value yet and the variance value yet because it is it's a very lengthy process. Okay, so if time permits, we'll do it. Otherwise, I'll make a short video of the derivation and send it to you. Okay, so this PDF is a very common PDF. You can see it all over the internet also. So it looks like this. This is the value of x, and this is fx of x, the PDF. Then this PDF has a bell shape. Okay, this is a bell shape. Okay, and these will represent the mean values. Sorry, this will represent the sigma square, whereas this line here would represent the mean value. So this will be mu here, this point here, and this will be your plus sigma square, that is variation in the positive direction. This will be negative sigma square. The portion which I am shading, okay, the portion which I have shaded, these are known as the outliers. This is just for your information. Outliers means they are outside the variance also. Okay, these are known as the outliers. If this mean value here, mu, is 0, then this bell shape just becomes a normal PDF. That is, it is Gaussian, but with a mean 0. Okay, so I hope that was clear. I'm stating I'm not deriving it. I'll make the short video and send it to you. Okay, or if time permits, then we'll do the derivation in the class itself. Okay, so this is a very important PDF. So for the normal distribution, let me write this here. For the normal distribution, the PDF can be written as fx of x. Before that, there is another variant of the normal distribution for which the mean is 0 and the variance is 1. So in that case, we write the normal distribution as 0, 1. So this variant of the normal distribution where mean is 0 and variance is 1 is the one that is used a lot. It is the most popular variant. Okay, and in this case, the PDF fx of x just simply becomes, now if I scroll up and show you that this is the PDF, 1 by sigma root 2 pi. So if the variance is 1, this sigma becomes 1, right? The mean is 0, therefore this mu becomes 0, and this sigma also becomes 1. So all we are left with is 1 by root 2 pi exponent of minus x square divided by 2, right? So for the normal distribution where mean is 0 and variance is 1, the PDF is very simply 1 by root 2 pi e raised to minus x square divided by 2, and this all happens for minus infinity less than x less than infinity. Okay, and you can always find its PDF by just doing the normal procedure, that is integrating from minus infinity to some value x, and you'll have fx of x dx, right? Therefore, in this case, fx of x will become minus infinity to x 1 by root 2 pi e raised to minus x square by 2 dx, and if you integrate this, you will get your CDF value. Okay, so that is of the form e raised to minus ax. Okay, so you will get your PDF. Okay, so I'm not doing the derivation like I said before, but I can always derive and send you the derivation. But what is important for us is to use this in solving the numerical values. Okay, next, so these were the PDFs. The PDFs which we have done till now were the continuous PDFs. That's why we were integrating them. So the uniform random variable, the exponential random variable, and the Gaussian random variable, these are the examples of uniform random continuous random variable, and that's why the PDF CDF were being integrated, right? Now we'll look at a few of the discrete random variables. Okay, so there are few which are specified in your syllabus. Please note that there are many random variables, but we are restricting to the ones only specified in your syllabus. Okay, so the first kind of discrete random variable is known as a Poisson random variable or Poisson distribution. The application of this random variable is in general to find the telephone calls. So if you are in a call center trying to predict how many calls you will get for a day, then you can use this Poisson random variable. Of course, it has many other applications also, but this is one of the most practical one. Okay. So this is defined as if x is the Poisson random variable, then pk or p of k, p subscript k is defined as b raised to k divided by k factorial into e raised to minus b, and k is from 0 all the way till infinity, and b is greater than 0. Okay, this is how the Poisson random variable is defined. For us in the syllabus, we need to know what this Poisson random variable is. The derivation is not there. We need to use this in solving the numericals also. Okay, so we are not going to do how we are getting this p subscript k. Why is it like this? Okay, so we are not doing that. Okay, the PDF of this random variable, that is fx of x, will be, since it is discrete, you'll have a summation for k equal to 0 to infinity p subscript k impulse function delta of x minus k, where x is the random variable value and k is from 0 to infinity. Okay. And its CDF value, that is capital Fx of x, is k from 0 to infinity p subscript k. Since there is an impulse function in the PDF, in the CDF we deal with the unit step function, and you'll have x minus k. We can always derive and find out, which again I'll be doing in the form of a video, or if time permits we'll do the derivation. Its mean value mu x and its variance value happen to be the same value, which is equal to b. Okay, so in different books and over the internet, you will see different notations for this Poisson random variable. Okay, but this is the notation that I am using. If you are comfortable with any other notation also, that's fine. Okay, sometimes instead of that k, there are some people who have used alpha. Instead of b, they have used beta. So there are different kinds of notation. So in that case, your equation would look like this. You'll have beta raised to alpha e raised to minus beta divided by alpha factorial. Okay, so there are different ways, but I'm sticking to the one which I have written. So this is one of the important uh, you know discrete random variable, the Poisson random variable. There are many others as I've specified, but we'll restrict ourselves to this. The second one is known as a Bernoulli's random variable. I hope you've heard this name, Bernoulli's. It is used. It is one of the most basic rules, Bernoulli's rule, which is used in probability. So when we toss the coin and we get heads or a tail, that is basically Bernoulli's random variable. The term binary, where you have two options, 0 or 1, is basically the Bernoulli's random variable. Right? So it is a discrete random variable, and it has only two outcomes. Okay, it's a discrete random variable with two outcomes, and the two outcomes are 0 and 1. Okay, and the probabilities that 0 and 1 have, so 0 has the probability of p, and 1 has the probability of q, which is 1 minus p. So that's how we find the heads or a tail. So if heads probability is 0.5, then the tails probability is also 0.5, 1 minus 0.5, right? So this is how we can write the uh, Bernoulli's table. So you have xi and you have the corresponding probability. So xi could be 0 or it could be 1. So the corresponding probability for 0, we can write, let's say, P, and for 1 we'll write Q. You must note here that in some books it is the other way around. Some people write it Q and some people write it P. It doesn't matter. The other one just has to be the 1 minus of the previous value, right? So you could write it in both the ways, right? So I'll just to avoid confusion, I'll just write it as P and Q, where where Q will be 1 minus P. Okay. So the PDF of this Bernoulli's random variable, that is fx of x, will be, since it is discrete, you'll have a summation for I equal to 0 to 1, and you'll have pi delta of x minus xi, delta of x minus xi. So you can actually find the summation. So if you put the value 0, you'll get p0 delta of x minus x0 plus the second value, which is 1, p1 delta of x minus x1, right? And now we can put the probability. So for the probability for 0, which we have written is p, so you'll have p delta of x minus x0, and that value is 0, so you'll just have delta of x, plus p1 is nothing but q delta of x minus x1. So you can only move the PDF by only one value, so x minus 1. So you can write the PDF in that form also. From here you can also find the CDF, which is fx of x, which will be integral for I equal to 0 to 1, summation from I equal to 0 to 1, pi unit step of x minus xi. Right, so you can find the CDF value. So I'll just directly give you the answer here. You can always do the summation part putting 0 and 1. So the CDF that you will end up getting will be p u of x plus q u of x minus 1. Right, so it is similar to the PDF value. Only thing that instead of the delta function, the impulse function, we have used the unit step function. Okay. So like I said, there are more such random variables which you can encounter. Okay, I think a Laplace random variable is also specified in your syllabus, but it is not much used. However, that you can find in my notes, or you can find it in the book or over the internet also. But what I intend to do first is the ones which are most commonly used. Okay. So definitely from your exam point of view and in general also, you must know the uniform random variable with the derivation of mean and variance. You must know the exponential random variable with the derivation of its mean and variance. You must know the Gaussian random variable, not in the form of its derivation, but more in the form of its application. Very, very important. Okay, so we will be doing numericals based on its applications, and you will see how that is used. Then in terms of discrete random variables, I would say the most important is the Poisson random variable. I have not seen many numericals based on it. Okay, but there could be any numerical. We'll solve a numerical based on it as well. Okay, so these are the ones which are mostly used, right? So I would expect you to be doing the same. Okay, so let us solve one problem based on this random variable. So the module 1 wise, there is just a small part of condition random variables which remains, and once I finish that, then your module 1 is over. Okay, so another lecture is enough to finish module 1. Okay. So let us take this numerical. So the question is, determine the mean and second moment, that is E of x square, for the Bernoulli's random variable, and verify the results using the characteristic function, right? So like I told you before, you can also use the characteristic function to find the mean and the variance value. For the mean, you have to take the characteristic function, find its first derivative, substitute omega equal to 0, right? So problems based on that we are going to do, and we'll see that the exponential random variable and uniform random variable, for which we have done all these parameters, can also be derived using the characteristic function, right? So that is exactly what the question is. Okay, so let us first write the Bernoulli's random variable in the form of a table. It's a discrete random variable. So we'll have xi, we'll have pi. The two values you can get is 0 and 1. Let 0 have q and 1 have p. You can also interchange it, it doesn't matter. So the table looks like that. Okay, so the mean value mu x will be I going from 1 to n, if you want to write it, or 0 to 1. So let me write it as 0 to 1, and the mean value is x fx of x dx. So since this is a probability mass function, you'll have xi pi, right? So now substituting the values, first you will get x0 p0 plus the second value x1 p1, and x0 is 0, p0 is q, x1 is 1, and p1 is p. 0 into q will give you 0, so you'll have 0 plus 1 into p, which is p. Therefore the mean value of a Bernoulli's random variable mu x is just p. So it will correspond to the probability that you will get for the value 1. So if you would have if you would have kept the probability as q, the mean value will come as q. Okay, so it depends on how you format your table, right? Okay, next we need to find E of x square, and that is defined as I equal to 0 to 1, and E of x square is x square fx of x dx. So you'll have x square pi, right? So this will be again 0 square dot q multiplied with q plus 1 square into p. Therefore E of x square will just be p. E of x square will also be p, right? So even though it is not asked, we can find the variance value, which is E of x square, which is p, minus mu x the whole square, which is p square. So you'll get p into 1 minus p. That will be the variance value. That will be the variance value. Okay. If you want to also rewrite it, it just occurred to me. If you look at the table, q in that table here, q can also be written as 1 minus p, right? Therefore in that variance value, I'll just make the modification. I can also write sigma x square as p, and 1 minus p is q. So I can also write the variance as p into q, because there are only two values there, right? So now we are asked to verify the same using the characteristic function. So the characteristic function for the Bernoulli's random variable phi x of j omega is given as q plus p e raised to j omega. Okay, this I have just given you the equation. I would want you to go back and actually derive this equation, right? So take the equation for the characteristic function. Okay, the e of e raised to j omega, that is e raised to j omega. So let me write this here. So you can find phi x of j omega is e of e raised to j omega x, and which is integral e raised to j omega x fx of x dx. right? So this is a discrete random variable, so use the summation, right? Using that, I would want you to derive this characteristic function which I have written here, okay? And see that Bernoulli's random variable has that, okay? The aim here is to find the mean value mu x, and mu x is e of x. So just to make it more clear, it is e of x raised to 1. So therefore we need to find the derivative d by d of j omega of phi x of j omega, and then substitute omega equal to 0, and substitute omega equal to 0, right? So therefore the mean value mu x would just be d by d of j omega, and phi x of j omega is q plus p e raised to j omega, and once you find the derivative, substitute omega equal to 0, right? So when you do that, you should get the answer mu x equal to p. So I'm skipping one step here, and expecting that you would be finding that derivative, and find out that mean value will be the same as the one that we found beforehand. Okay, please go back and do this. Okay, for e of x square, it's just an extension d square by d square of j omega of phi x of j omega. So e of x square, and here you will have to put omega equal to 0, for omega equal to 0, right? So e of x square is just going to be d square by d square of j omega, and phi x of omega is q plus p e raised to j omega. Find the double derivative and substitute omega equal to 0, right? And your answer should match, and you must get p. So in both the parts, on the left hand side and the right hand side, I've actually skipped one step, and I'm expecting you to do that and see that the mean value and the e of x square value are one and the same. Okay. So in the next class, we'll be doing the conditioned random variable, which is the last part, and I will also be making one table for you, where for each of these distributions, that is the random variables, I will be giving the probability density function, which is the PDF, its corresponding mean value, and the corresponding second moment. And once you have these two, you can always find the variance value. If the time permits in that lecture, we'll also write the characteristic equations for all of these random variables, which will also help us in finding the mean and the variance values.